Hello, in this booth today we are showing our latest evolution in our inertial measurement unit portfolio, our improvement in the full scale for the acceleration functionality. Traditionally, all the IMUs are limited to 16G or 32G full scale. We are bringing to the market now with the LSM-6DSV 80X and the LSM-6DSV 320X the capability of adding a full scale all the way up to 80G or 320G, depending on the part number. This enables a variety of new applications. So now you're able, instead of saturating the signal when there is an impact, understanding exactly what's happening with the impact to the final product. If you take the example of a helmet and the IMU is mounted on the helmet, you will be able to determine if an impact is an actual concussion or it's just a small hit. And to demonstrate that, we are using an impact kind of game where we've been given a target and then we try to hit that target of acceleration. We are using to do so our Sensor Tile Box Pro with the DIL24 for the sensor connected to it, and the device is here in the middle of this board. It's a tiny 2x5 by 3 millimeter IMUs. Inside we have an impact sensor. We have a gyroscope, a low full-scale accelerometer that will allow you to determine small motion, and then the high G accelerometer as well. I've been given a target, so my target now is 192G. Let's try to hit it. I do a trial run first. So 222, close enough, and now I know how much do I have to hit. 253, a little too much. This was 41. Final score is the distance between my best shot and the actual target. So I didn't do great here, but some people can really hit close to what the final result is. Now, I mentioned the high G impact accelerometer, and that's what we showed over here. If I put the hammer down, I'm still sensitive enough in our IMU to sense a small movement. If I tap on the table, you can see here on this GUI that the accelerometer actually senses even small displacement. So big impact with the high G accelerometer, small displacement with the low G accelerometer. So we just hammered our target with our mallet, and we see that the low G accelerometer experienced a big spike that saturates the full scale. On the second row, we see the high G accelerometer instead, measuring exactly that impact. Now, the low G accelerometer is always on and sensitive also to small displacement. If, for example, I knock on the table, you see those little knocks being sensed as well. And the capability of having these two sensing elements tuned to two different scales give you really the flexibility of monitoring a slow movement together with big impact, retaining meaningful information from both. This device, together with all the family that is part of the LSM-6DSV, has some embedded AI capability. So there are many embedded features that we have traditionally in our motion sensor, the step counter, the tap, and the double tap. But we want to open the programmability of those sensors to our end user. And right now with functionality like the finite state machine, the machine learning core, or the adaptive cell configuration, the user are able to program and make the sensor more tuned to their own application. Things that would traditionally be computed in a microcontroller connected to the sensor now can be computed in sensor directly. Finite state machine is a flow that the user can program, a myriad of states that you program, and you program the transition between those states. Machine learning core is a decision tree classifier that can be programmed with machine learning techniques, so it involves data acquisition, data labeling, and then the final synthesization of the inference, and we provide tools to support you in all these steps. And the automatic cell configuration, the adaptive cell configuration, is the capability of the sensor to move between configuration states depending on the output of these two previous functionality, the finite state machine and the machine learning core. A fourth capability that our sensors enable in our DSV family is also the sensor fusion low power. So you have always the option of streaming raw data from our IMUs, but now we also compute the gain vector directly in the sensor itself, and you can output the quaternion directly from the sensor.